Okay, hello, and this is my first go around at recording the screen of my iPad while I use this fancy Apple Pencil. Let's check it out here. Okay, so there we are. Okay, so this is how I'm hoping to do my little mini lectures. You can give me some feedback on the sound quality, the image quality, anything else to do with this. Okay, and these are meant as not really a drop-in replacement for regular live lectures, but to give you that kind of background and said in words that your instructor is going to be using for the rest of the semester. So I think a little nicer than getting it directly from the textbook or something like that. Okay, so to the subject at hand. We're going to talk a little bit about significant figures. We're going to talk a little bit about uncertainty, precision, a little bit about the metric system and units, and then we'll wind up all hopefully within about 5 minutes here. So, as the slide says there, estimating or knowing the uncertainty in a measurement is fundamental to experiments and so to science and, of course, physics in general. So, first off, if you're looking at a number like the one that I've circled here, 3.45 meters, right? So that M right there, that's meters. That's the standard unit of length in the metric system, and it's one that you'll be using a lot. You might want to be familiar with a couple of the prefixes. There's a lot in the metric system, but the ones that I'm really going to expect you to have in your brain are things like kilo. In this case, add that to meters. And kilo is 10 to the third, okay? And in addition to that one, you might want also to know centi. Oh, my good handwriting, preserved by the Apple Pencil. Centi is 10 to the negative 2. So in other words, 0.01 meters, okay? It's about 2.5 centimeters in an inch, which is the unit of measure that we're a little more familiar with here in the United States. And then finally, the last prefix in the metric system that I'd like you to know is milli. So we could apply it to meters, millimeters. Milli is 10 to the negative third. So 0.001 meters is a millimeter. Those three, kilo, centi, and milli, are the ones that I'm going to expect you to have in your brain. The rest of them, mega, giga, yocto, deci, all of these other more exotic ones that we don't see quite as often except in specialized cases usually. You don't have to memorize. If I happen to bring them up, I will apprise you of that on quizzes and exams. Okay, so going back to this number, 3.45 meters. One, always use the units. Always, okay? Even if it's like counting something like 3 people, always say people. That's the unit of that count. So bare numbers, unless you're in a very specialized kind of situation where the context is known by everyone who's ever going to read that thing that you just wrote on the page, well, you need to indicate what it's measured in. Is it meters? Is it kilometers? Is it centimeters? Is it millimeters? Is it megameters? Okay, so just always use the unit. I will definitely assign some points to using the appropriate units. Not a ton of them, but, you know, they're important, so I'm going to expect them to be there. Now, in terms of precision, well, that's what this other thing is talking about, our last significant digit. What does that mean? Okay, well, what that means here is that this 5 right there, okay, that 5 is the last significant digit, which means that it defines the implied precision of this number, right? So if I write it specifically 3.45, what that's telling you is that I know that number down to the hundredth of a meter. In other words, down to the sort of centimeter. But that 5, well, it might be 6, might be 4. If we're a little less precise, though it's hard to tell just from the way this is written, you know, I'd say, oh, it could be as high as 7 or 8, or as low as 2. But that's the last digit, last significant digit. That's the one, only one in that sequence that should be uncertain, right? The 3 and the 4 are more or less fixed, known, and assumed to be correct in sort of implied in writing it this way, okay? So that's the implied precision. You don't want to use imply more precision in writing a number than you actually mean. So I could write this with far more significant digits. Trailing zeros, as it turns out, are significant. I could write it like this, right? Numerically, this is saying the same thing, but in terms of precision, in terms of the uncertainty that's implied by the way that I wrote that, well, now I'm saying I know it down to the, let's see, 100,000, 10,000, 100,000, millionth. I know it down to the millionth of a meter, which seems unlikely unless I've got a really excellent measuring tool at my disposal. Okay? So don't use more significant digits than you need. Don't just write all 12 digits that show up on the face of your calculator when you type in some numbers for a calculation, right? Look at the numbers that you're feeding into the calculation, look at the precision of those numbers, and from that you can know how many significant digits to report in your number, okay? So in this number right here, we've got 3 sig figs, okay? And that counts all 3 digits you've got there. Like I said, if you have trailing zeros like this, those all count. If you have zeros that are sort of somewhere in the middle, bracketed by like, if I had a 0 in there or something, that 0 would also be significant. The only zeros that typically don't get counted as significant digits are, this is a kind of a funny corner case, if you have 340 and you don't put a decimal point there, typically you take that as having 2 significant digits, and this trailing 0, because it doesn't come after a decimal point, is not considered significant. If you want to make sure that somebody knows that this is 3 significant digits and you measured it to 340 exactly, well, then typically the practice is to just stick a little decimal right there, okay? And then this would be read as 3 significant digits, okay? Now, all that said, I'm not going to be a big stickler for these. I think understanding the precision of numbers is important, and you'll run into this in your physics lab course as well, particularly there where you're dealing with experimental data sets, multiple numbers reported to a certain precision. For example, if you have a meter stick, you're not going to be reporting anything, any significant digits past like the millimeter level of precision, right? Because a meter stick goes down to about the millimeter, and not any more precise. You need a better tool to get any more precision than that, all right? So it is an important thing, but if you're off in terms of, turning in a problem set or a problem on an exam in this class, if you're off by a significant figure, 1, I'm not going to get too bent out of shape about it, but don't go crazy, right? Again, right? Don't give me so many trailing zeros or like 12 digits when you're nowhere close to that level of precision. Okay? We want to reflect reality in the numbers that we write. So, let's take a look at this situation. All right? So, when multiplying or dividing in a calculation, and let's take a look at that. And for some reason we've got some missing equal signs there. I guess we're dealing with some translating PowerPoint files from Windows to Apple stuff here, but I think we'll soldier through. Right here, we're given the radius and height, so the height and radius of this disk or cylinder. And if we wanted to compute the volume of that cylinder, we would have to break out. Let's see if it's going to render. Yeah, see, they're going to drop all the minus or equal signs on us, and a few other things. So let me actually just write this in a little bit. We'll annotate. And we're missing some things here. We need a pi. Okay. And this will be a pi. And now we're good. Okay. So the volume equation for a cylinder or a disk is pi r squared, so that's the area of the circle, and this is its depth. So you take the circle and you sort of stretch it by h, right? And if we put in all that, we have matching units here, so millimeters and millimeters. That's nice. We don't have to do conversions. If we put all that in, we punch it into our calculator, I think you should get this. And I've kept a ton of extra significant figures here, right? How many should we actually be reporting? Well, when you're multiplying numbers together, so here we're multiplying 2 factors of r, because we're squaring it, and a factor of height. Well, we're just multiplying 3 numbers together. And so when you have that situation, or if you're dividing, okay, depending on the calculation you're doing, well, what that means is you want to round to the least precise number that you're feeding into that calculation. So here, that's this one, right? We have 1, 2, because we've got that trailing decimal, 1, 2 significant figures. So the final answer should be reported to 1, 2 significant figures as well. Okay, so the volume we would actually box and report would be rounded to 14,000 millimeters cubed, or cubic millimeters. Okay, and 14,000 cubic millimeters is not a particularly intuitive unit. So, that's maybe something we could adjust. We could turn it into cubic centimeters or something like that. But for now, we'll just leave it as is, okay? So, least precise number. Now, when you're adding or subtracting, the situation is much the same. You're still sort of being constrained by the least precise thing, but there's a little bit of a wrinkle, okay? So, say we're dealing with these 2 numbers right here, and we are subtracting them. Well, you can see that for one thing, one of them has 4 significant digits. So this 0 doesn't really count for sig figs, but these 4 things are counting for sig figs. And then we've got 2 sig figs up here. So if we went by the previous rule, we would say, okay, well, the thing that we report would have 2 significant digits. And, actually, that would get you pretty close here, okay? But there is a slight difference when you're adding and subtracting versus multiplying or dividing. And that's this, okay? So you'll note that the thing I'm reporting here has only 1 significant digit, and yet the least precise thing has 1, 2, okay? So what gives? Well, what you're doing when you're adding or subtracting is, if you think about what this actually works out to be, so you subtract 0.2567 from 1.2, so you're coming down to like 0.9433, something like that, okay? And the reason that we've rounded to the tenths place here is it's because it's the most precise digit that both of these numbers hold in common, right? If you come down here to the hundredths place, well, there's no corresponding significant digit in the top number here. And so that means that we don't want to include it down here because we'd essentially be adding precision. We'd be saying, oh, we know it down to the 100th of a meter, rather than only really knowing it down to the 10th of a meter like we do in this number. Okay? So, those are the formal rules. I'm not going to go too much in depth beyond that. There are lots of little wrinkles to significant figures and implied precision and things like that. But this stuff is important. Just to give you a quick example, if you have a number like this original one that we were talking about, and instead of reporting it to that precision, I report it to, say, like this precision, where I want that thing accurate down, or I'm implying its precision down to the 10,000th of a meter, okay? So that's down to the 10th of a millimeter. And I think anybody who's done any machining or building anything, or even just sort of thinks about it for a little while, even if you haven't, if I were to put together a set of plans, and I were to put some dimensions on those things, and I were to write everything in terms of precisions that implied that I only really cared about the dimension of whatever side of my thing, down to the hundredth of a hundredth of a meter, in other words, down to the centimeter precision level, that doesn't require fancy tools to get down to that precision level, right? A meter stick, and you're done, right? You can do that measurement, you can cut the piece of wood or whatever, and you're good. Now, if I write it this way, okay, and I say, hey, machinist, go make me one of these things, okay? If I really only care about it down to this precision, right? Well, that's not what I'm telling the machinist. The machinist looks at this and they say, okay, he wants it down to the 10,000th of a meter precision. So I'm going to break out some pretty fancy tools, and it's going to take me a lot longer to knock this thing together than it would if I was reporting my precision or implying my precision accurately. Okay? So let's wind up there. I may have gone on a little bit long on all this stuff, but hopefully you find it uswe'll, and we'll try to keep the next ones a little more succinct. Thanks.